Hey everyone. Math 408 complex analysis is not required for this class, but a little bit of knowledge of complex numbers is required. Now, I don't expect that you know a whole lot about it, so what I'm going to do is just a quick kind of overview of the material regarding complex numbers that you need to know for this class. So let's say it like this, some words about complex numbers. Maybe you've seen this stuff before, maybe you haven't. So first thing, if we take a complex number, so z, remember we can write any complex number in the form z equals a plus bi, where I equals the square root of -1. So if this is an element of C, then we can represent Z in what's called the complex plane. And so what we do is we draw a plane that looks just like the usual plane. And what we have is a real axis. So I'll label it the x-axis, but we consider this the real axis. And then we have the complex axis, which I label as the y-axis. And so if we have z equal to a plus bi, what I do is I go over a units on the x-axis, the real axis, and then I go up b units to the position bi on the imaginary axis, and then our complex number then sits in the plane like that at a plus bi. So you can think of it, you can sort of think of a correspondence between, in fact you can, if you're careful, think of a correspondence between R2, right, where all the elements are written as ordered pairs, and C, the complex plane, where you go from A comma B, it corresponds to A plus BI in the complex plane. All right, so there's the ideas. We can draw a picture of the complex plane and represent elements in there. Right, so let's just say the horizontal axis is called the real axis, and the vertical axis is the imaginary axis. So this just gives us a way to picture all the complex numbers. The modulus of z is, and we write it using absolute values around z, and it is going to be the distance from the origin to z, right? And so how do you compute that? Well, you do it the usual way. The modulus of z is the square root of a squared plus b squared. So you just use the usual distance formula to measure distance from the origin to the point in the complex plane. Now, using polar coordinates, let's see how that would work. Let's see, what would that be? Right, we could take an angle right there, and then what we would get is that z equals the length of z, or the modulus. I sometimes will slip and say the length. The modulus of z times cosine theta plus I sine theta, where this angle right here is theta. Okay, so I'm going to have to erase that picture, but remember then that just as when you're working in the plane, you can write an ordered pair. So if you have an ordered pair x comma y, there's a way to go back and forth between the ordered pair and the complex represented, which would be r cosine theta, comma r sine theta, right? And so this is just using the a plus bi notation, right, rather than the ordered pair notation. Now, from calculus, if you go back to calculus 3, so calculus, one thing we know is that e to the x can be written, right? It's got the power series representation, sum n equals 0 to infinity, x to the n over n factorial. And so, e to the I theta, so I'm going to substitute, that's equal to the sum n equals 0 to infinity, I theta to the n over n factorial, which, if you were to actually write this out, so let's see, when n equals 0, you just get 1, and then you get plus, well, it'd be I theta to the 1 divided by 1 factorial, plus, I'm going to write out a few terms here, plus I theta squared over 2 factorial. And, you know, officially there's a 1 factorial down here, and officially there's a 0 factorial here. Remember, 0 factorial is equal to 1, but let's not crowd our picture out too much. Then it would be plus I theta cubed over 3 factorial, and you just keep going. Now, what I want to do is split this into the even terms and the odd terms. So this is equal to 1 plus I theta squared over 2 factorial plus I theta to the 4th over 4 factorial plus blah, blah, blah. Plus, then there's the odd terms. And those odd terms will be an I theta plus I theta cubed over 3 factorial plus I theta to the 5th over 5 factorial, and so on. All right, so what have we done here? We took e to the I theta, plugged it into our power series representation for the exponential function e to the x, wrote out the terms, and now I'm separating it into the even powered terms and the odd powered terms. And then let's notice what happens here. In this first piece, what do we know about I squared? I squared is equal to -1. I fourth is equal to +1. I to the 6th is equal to -1. So this is actually an alternating series. And it looks like this. 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial plus, I'll write one more term here, and actually it's minus theta to the 6th over 6 factorial, and so on. So it's an alternating series. Same thing here. If I pull an I out, is that what I want to do? Yeah, I want to pull an I out, and then I'm going to get theta minus theta, theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus theta to the 7th over 7 factorial, and so on. Another alternating series. And now you need to remember back to calculus. Who is that one right there? That's cosine of theta. Who's this one inside the parentheses? That's sine of theta. And so this is equal to, it's equal to cosine of theta plus I sine theta. Right, so let's collect what we have here. E to the I theta is equal to cosine theta plus I sine theta. That formula right there, that's known as Euler's formula. And maybe you've seen this before. It's okay if you haven't. Right? It's a true fact we just derived using a little bit of knowledge of power series that this exponential function e to the I theta is equal to cosine theta plus I sine theta. Now, remember, we had the polar representation. So what did we have? I had z is equal to modulus of z times cosine theta plus I sine theta. And so now, if I make use of Euler's formula, here's what we get. We get z is equal to modulus of z times e to the I theta. So this gives us an exponential or polar coordinates, this is really polar coordinates, version or representation of our complex number z. Z can be expressed as modulus times the polar coordinates, but we're using the exponential form of the polar coordinates. And this is a useful way to think of it, and we'll see why. So let's say, so now, suppose we have a couple of complex numbers. Let's call them z1 and z2. Right, so these are both complex numbers. Then we can write well, okay, so z1 can be expressed as, well, let's write it out. So this is z1 equals a plus bi, and z2 is c plus di. And then using our polar coordinates, so we'll say or, right? So you can always use the a plus bi, the standard standard way to represent your polar coordinates, or you could, your complex numbers, or you can use polar coordinates. So that would be z1 equals modulus of z1 times e to the I, let's call it theta 1, and z2 equals modulus of z2 e to the I theta 2, where now who is theta 1 and theta 2, right? So where theta 1 is equal to, oh, I guess it's actually tangent. Tangent of theta 1 is equal to b over a, and tangent of theta 2 equals d over c. So that's just the usual polar coordinates conversion. Okay, now, and here's the point. If we want to multiply these complex numbers, so we'll say now, if I do z1 times z2, and I use this formulation right there, all right, that's going to give us an a plus bi times c plus di. Okay, so that's going to be an ac minus bd. I'm just going to FOIL this out. Plus AD, well, plus BC times I. Right, so there's the complex number, right? Multiply these out, you get a complex number, and there it is. But if instead I used the polar coordinates formulation, it gives us a clearer understanding of what's going on. So if I do this, what I'm going to get is so let me just write this out. And then we just have to remember how to multiply exponential functions. And so what we get is modulus of z1 times z2 times e to the I theta 1 plus theta 2. And the picture of what this looks like helps us see how clearly, it gives us a clear picture of what it means to multiply complex numbers, right? So let me draw the picture here in the complex plane, right? So let's say I've got Z1 is right here. Yeah. And let me put Z2. It doesn't need to be a right. I kind of made it look like it's a right angle. It doesn't have to be. So, yeah, something like that. So it may or may not be a right angle. That part doesn't matter. So there's Z2. And of course, here's theta 1. Here's theta 2. And then, remember, that distance right there, that is the modulus of Z1. That length right there, that's the modulus of Z2. And now notice what this tells us. When I multiply, what do? Well, first we multiply the moduli, and then we add the angles. So theta 1 plus theta 2, theta 1 plus theta 2 is going to give me, let's see how much that is. Well, it's about like that, right? Where I don't want to crowd the drawing too much, but this total, I guess I can do it up here, that angle right there is theta 1 plus theta 2. And so Z1 times Z2, the multiplication can be viewed this way. What do? You multiply the moduli and you add the angles. Right, so let's say it like this. Geometrically, complex multiplication is modulus, let's say modulus multiplication combined with angle addition. All right, so this gives us a nice geometric picture of what complex multiplication is. So, for example, let's say that Z is 1 plus I, and W, another complex number, is going to be root 3 plus I. That it? No, yeah. Yeah, okay. So let's write down the complex representations of those two. So let's see what we get. What I want to do is write each of these in polar coordinates now. So the modulus of Z is root 2, and the angle is going to be, tangent of theta is going to be 1. So theta equals pi over 4. So that means that Z can be written as root 2 e to the I times pi over 4. And now for W, the modulus of W is going to be 3 plus 1, so I guess it's 2. And then tangent of theta, the angle here, is going to be 1 over root 3. And so theta is equal to pi over 6. And okay, so now, so let's write it out. So I've got my Z is right there. My W is going to be a 2e e to the I times pi over 6. And so now, when we multiply z times w is going to be, in polar coordinates, it'll be a 2 root 2 times e to the I times pi over 4 plus pi over 6. Common denominator is what? 12. So 2 root 2 e I 3 and 2. Oh, 5. What is it? 5 pi over 12? I can't do it. Pi over 4. Sorry, I'm spacing out here. Plus pi over 6 multiplied by 3, so that's a 3 pi over 12, and that's a 2 pi, yeah, 5 pi over 12. 5 pi over 12. Right, so that gives us a nice picture of how it works in complex multiplication. Let's do some more examples and we want to see why this polar coordinates representation can be useful. So let me start over here, and I'm just going to do a couple examples. So let's find all z in C such that z cubed is equal to 2i. So I want to solve this complex equation right here. And I'm going to make use of polar coordinates in this case. So first, let's write z in polar coordinates. So it'll be modulus of z times cosine of theta plus I sine of theta. And let's also write 2i in polar coordinates. So that's going to be, let's see, the modulus is 2. And then, what am I doing here? Oh, right, 2 times 0, of course, 0 plus I. Sorry. And then what we have, if we take a look at this equation right here, then the z cubed is going to be, well, it'll look like this. Modulus of z cubed cosine 3 theta plus I sine 3 theta has to equal 2 times 0 plus I. So what does that tell us then? So that tells us then, so we can say, so the modulus of z has to equal 2 to the 1/3, right? Because we can equate the moduli. And then we also know that cosine of 3 theta has to equal 0, and sine of 3 theta has to equal 1. So, so we have cosine 3 theta equals 0, and we have sine 3 theta equals 1. So what does that tell us then? So what does the solution look like? Well, it tells us that 3 theta has to be, well, let's write it like this. So 3 theta has to be, so it's got to be pi over 2 plus, yeah, plus integer multiple of pi. Right? Oh, whoops, wait, what did I say? There's a second part. So in solving this, so what choices give us 0 here? It is going to be, so when is cosine equal to 0? it's equal to, or it occurs at integer additions. Sorry, I'm flubbing this now. So cosine 3 theta equals 0 corresponds to that equation right there. Also, when is the sine of 3 theta equal to 1? So that would tell us that 3 theta has to be, so that occurs at pi over 2 plus, let's say, 2 times, should I use a different letter here? Yeah, I guess 2k pi. All right, so this equation right here corresponds to that solution there. So we need these to happen simultaneously, which means that that is the equation that solves both of them simultaneously, right? The even multiples of 2 pi will encapsulate these ones right here also. Okay. So now let's figure out what theta has to be. So we can say thus, theta has to equal pi over 6 plus 2 k pi over 3, right? And this gives us all possible solutions. So when k equals 0, so let's look at k equals 0, that corresponds to pi over 6. When k equals 1, that corresponds to pi over 6 plus 2 pi over 3, which is going to be, 5 pi over 6. And then when k equals 2, what we get is pi over 6 plus 4 pi over 3. And so that's going to be a multiplied by 2, that's 8 plus, that's going to be 9 pi over 6. Right, which I guess we can simplify as 3 pi over 2. And let's do one more to see what happens here. When k equals 3, we get pi over 6 plus plus, what do I do in k? That's a 3, so it'll just be 2 pi. What? Oh, sorry, 2 pi. The 3's cancel, plus 2 pi. Which, in terms of angles, is the same as pi over 6. And this is going to repeat itself, so these 3 solutions right here, or these 3 angles, give us 3 distinct solutions to our original equation. So the solutions Z0, let's call it, that's going to be 2 to the 1/3 times cosine pi over 6 plus I sine pi over 6, which is 2 to the 1/3 times root 3 over 2 plus let's say I over 2. And then our next solution, Z1, that's a 2 to the 1/3 times cosine 5 pi over 6 plus I sine 5 pi over 6. Let's see, 5 pi over 6. Okay, so that's going to be 2 to the 1/3 times negative root 3 over 2 plus I over 2. And then the last one, Z2, is going to be a 2 to the 1/3 cosine 3 pi over 2 plus I sine 3 pi over 2, which comes out to 2 to the 1/3 times the cosine of that is 0, and that's -1. Oh, whoops, I lost my I. Sorry, that should be minus. And then, right, since this pattern repeats, this tells us that these three complex numbers here, and you can write them in either the a plus bi form or the complex form, those are the three solutions. And it's nice to see what this looks like geometrically. So I've got a pi over 6. I've got a 5 pi over 6. And so there's Z0. There's Z1. And then if you go out here, there's Z2. Right? So geometrically, these solutions live on a circle of radius 2 to the 1/3, right? And they're equally spaced. So geometrically, the solutions are, I don't want to say this, at equally spaced intervals on the circle with radius 2 to the 1/3. Okay, so that's a good place to stop here. You may or may not have seen this step before. This class is not going to focus heavily on complex numbers, but there is a reason to know this, and so we're going to see this in the very next lecture, that the set of complex numbers gives us certain important examples of groups, right? And so that's the point. We need to know a little bit about complex numbers so that we can learn about certain new groups, right, that come as subsets of the complex plane. Okay, so we'll see you later.